In any calculus textbook, you're going to find implicit differentiation following hard upon the chain rule. And the reason for that is implicit differentiation, in one sense, is just the chain rule. But in any event, it makes use of the chain rule to differentiate equations involving two variables. And in implicit differentiation, we treat one of the variables as a function of the other. All right? So there's a departure here. Up until now, we have differentiated only functions, and only functions expressed explicitly in terms of the variable of differentiation. Now, we differentiated with respect to x. Well, x squared, the cosine of x, the square root of x. Everything was in terms of x, even if it was a composite function. Now, we're going to differentiate whole equations, which may or may not represent functions, certainly in x or in the variable of differentiation. It is implied, right? It's implicit differentiation. It is implied that the second variable is a function of the first, so that any operation additionally performed on that second variable creates a composite function, bringing the chain rule into play. Let me just demonstrate that. All right, very simply, the derivative with respect to x, d dx of x squared, is 2x. However, in implicit differentiation, you're differentiating with respect to x. You may want to differentiate within an equation y squared. Again, it is implied that y itself is some function in x. So you have a function in x squared. You have a composite function. The derivative here is not simply 2y. It is 2y times whatever the derivative of that inside function is. The derivative, as we have seen recently, of the sine of x is the cosine of x. The derivative with respect to x of the sine of y is the cosine of y times dy dx. And, this can become a pain after a while. You may want to just write y prime rather than dy dx, and I'll probably do that as I get into these. But, again, implicit differentiation uses the chain rule. It's just that we don't know explicitly, in terms of x, what that inside function is. We are inferring that it is a function in x. If it were not a function in x, we'd be treating it like a constant, and the derivative would just be 0. Okay, so now let's take a look at the kind of problems we'll do. Again, in practice, we will differentiate whole equations with both x's and y's in them. And our strategy for finding dy dx, which is what we're going to do, find dy dx, will be, number one, differentiate every term with respect to x. Okay, let's take an example. X squared plus y squared equals 25. Now, I chose that for a reason. Just as a reminder, you should remember what that is. That is a circle. That is specifically the circle with a center at the origin and a radius of 5. And we know that a circle is not a function in x. It fails the vertical line test. But that does not change anything about the derivative. Remember, the derivative still and always gives us the slope of a tangent line. So, here we go. First step, differentiate everything with respect to x. 2x plus 2y, y prime, equals 0. Right? Second step. Get all of your y prime terms on one side and your non-y prime terms on the other. Well, here I'll take another thing too. I can divide both sides by 2. 0 divided by 2 is still 0. So I have x plus y prime equals 0. Y prime equals negative x. Last step, isolate the y prime. So y prime equals negative x over y. That is dy dx, or y prime. Now, suppose we wanted to do just a little bit more with that. Remember, again, the derivative always gives us the slope of a tangent line. Suppose we ask now, find the derivative, or find the slope of the line tangent to that curve, passing through the point 3, negative 4. Well, let's draw what we're dealing with here. Again, that is a circle. Radius 5. Center at the origin. The line tangent to that at the point 3, negative 4, somewhere around there. All right. Well, at the point 3, negative 4. Now, to find the actual slope of our tangent line, we're going to have to use both the x and the y coordinates of our point. So our slope here is negative 3 over negative 4, which is 3/4. All right, seems reasonable, certainly a positive slope. Now let's find the equation of that tangent line. It looks to us like the y-intercept should be below negative 5. Well, we know the slope and we know the point. So y minus negative 4, so y plus 4, equals 3/4 times x minus 3. So y equals 3/4 x minus 9/4 minus 4, which is 16/4, so minus 25 over 4. That is negative 6 1/4. Again, looks like a perfectly reasonable answer. That's